All right. All right. Hi, guys. Welcome back. We're all having a good last couple of weeks. We have only 2 weeks left of the semester, so time sadly is running out on us. And so many topics in number theory that we could discuss, but I want to make some sort of consistent presentation with you. All right, when we last left our heroes, we were talking about these primitive roots, and I gave you some exercises from chapter 9 to experiment with. Did you have any comments or questions on that, those topics? All right. Well, the analysis that we've done so far has helped us to know that there are primitive roots when you work modulo p, and we talked about how to adapt them if necessary to get primitive roots modulo a power of a prime p. That turns out not to be too hard. There's kind of one missing ingredient left, which is to know that if you're not working modulo a power of a prime, then you don't have a primitive root. At least I say that, but there's a couple of nuances that have to do with the prime too. So I want to make sure I get those details straight as well. So let me spin this around and show you some aspects about that part. See? Oh, that's the whole thing. There we go. Okay. So these primitive roots are cool. We'll be talking more today about the utility of them, but I've only been discussing them in the case where our modulus is divisible by just one prime. And now I want to show you that that's actually a necessary condition because things go awry when there's more than one prime dividing the modulus. So, theorem. If the modulus n is divisible by more than one prime power, let's say odd prime power, then there is no primitive root mod n. So in the language of group theory, what this is telling us actually is that when you look at the multiplicative elements mod n, then that group is not cyclic if n has got more than one odd prime divisor. This is why more than one odd prime. I guess I don't need to say power. Then it's not cyclic. And there's a couple of ways that I can show you this, so I actually want to show you both of them. One of them is to use the fact that, use a homework exercise that you guys worked on once before. And I'll remind you of the following property, a proposition theorem, just call it a theorem. If n is written as the product of two numbers that are co-prime, then with one exception, you will be able to find 4 distinct square roots of 1 among the multiplicative integers mod n. There exist at least, I should say, greater than or equal to, but anyway, I can at least find 4 congruence classes x mod n. They're going to end up being invertible, as you'll see in just a second, but I'll prove that separately. They'll all have the property that their squares are congruent to 1 mod n. Now that's going to be a problem because I'll show you on the other hand that if you have a primitive root, then you should only have 2 elements that are congruent, 2 square roots of 1. So just so you're keeping score here, when we had n being a prime, then we knew that there should only be at most 2 solutions to a quadratic polynomial. So here we're already seeing that that kind of result will fail spectacularly when you have a number that's got more than two distinct prime divisors. That's the situation up here. Now, I gave this to you as an exercise once before, and the rationale behind having it once before is that it helped you see a little bit about how squaring has something to do with finding factors. Finding square roots, in this case square roots of 1, is actually kind of tantamount to finding factors of a composite number. So what's the rationale behind this? I know that this is true because I can actually find these solutions. I do need to say here that I need A to be, let's just have A be odd, because I was talking about odd primes up in here. The prime 2 will work similarly, but there's a little twist that I said was an exception. So what's the solution to this? I will actually construct the 4 integers for you. Let x1 and let x1 be an integer that's congruent to 1 modulo a, and have x1 also be congruent to 1 modulo b. Now, I put 1 into both of these locations, but no matter what integers I put into these locations, you know from the Chinese remainder theorem that since a and b are co-prime, I can certainly find an integer x1 that will do this. So such an x1 exists. That follows from the Chinese remainder theorem. Then, what do I know about x1? Well, actually, let's pause for a second. You shouldn't be too surprised to know that there is an integer. Maybe you're already sitting at home thinking, I know what that integer is. There is obviously an integer that would be congruent to 1 more than a multiple of a, and simultaneously being 1 more than a multiple of b. You know what integer would do that? 1. So that's obviously a solution to this, but I'm going to set up a similar framework for the other 3 solutions. So now let's observe that because x1 has those properties, then x1 squared is congruent to 1 modulo both a and b as well. And so x1 squared is a number that's, well, x1 squared minus 1 is a number that's a multiple of a and it's a multiple of b. And since a and b are co-prime, that means that x1 squared minus 1 is a multiple of a times b. So a times b divides x1 squared minus 1. And that means that this number x1 is a solution to the original problem, to the problem of finding a square root of 1 modulo n, because n is a times b. So that was easy enough. Now the point is that I could replace the 1s in the top row by a minus 1 in either setting, and I will get more integers that will have squares congruent to 1. So I'm switching now to a different color. Similarly, if I choose, similarly with the number x2, that's going to be congruent to plus 1 mod a, but have x1 be congruent to minus 1 modulo b. Then such an x2 exists, again by the Chinese remainder theorem. This time I cannot tell you in just a symbol or two exactly what this integer is, but the Chinese remainder theorem at least guarantees that it's out there. But when you square this, now x2 squared is congruent to 1 modulo both a and b. So x2 squared is in fact the same as an integer that I described over here, or more generally, x2 squared minus 1 is divisible by both a and b, and therefore by the product, which is n. So x2 squared is a second solution to the problem. And then you can move on and take an x3, which is congruent to minus 1 modulo a, and congruent to plus 1 modulo b. It's another solution to the problem. And then the fourth is x4, that's congruent to negative 1 modulo both of them, and so x4 is congruent to negative 1 modulo n. So I've given you recipes for constructing 4 solutions to this problem. Now you do have to ask yourself whether or not those integers are different, whether or not there are different solutions to this problem in Z mod n. But in fact, for example, x2 and x4 cannot be the same mod n, because that would mean that their difference is a multiple of n. And if it's a multiple of n, it also has to be a multiple of both a and b. Well, it is in fact going to be a multiple of b. Both x2 and x4 are congruent to -1 mod b, so their difference is a multiple of b. It's congruent to 0 mod b. But when you look at x2 minus x4, x2 minus x4 will be congruent to 1 mod a, but this one's congruent to -1 mod a, so the difference is congruent to 2 modulo a, not 0. So if the difference between x2 and x4 is not even a multiple of a, then it's obviously not a multiple of a times b either. It's not a multiple of n. So the conclusion, therefore, is that x sub a is different from x sub 2, can't read my own handwriting, x sub 2 is not the same as x sub 4 modulo n. So those two would count as different solutions to this problem when you're working modulo n. And likewise with any of the pairs. I have x1 through x4 listed. I've told you how to create them. I know why they exist. Every one of the 4 of them is a solution to this problem, and they are all different. With one caveat, I did have to know here that 2 is not the same as 0 when you're working modulo a. And that's the reason that I threw the word odd in here. Actually, the entire proof would work just fine if the number a is an even number that's other than 2. If a is something that's divisible by at least a 4, or a 2 and another odd exponent, another odd prime that does not divide b, then I would still be all right. So really, I could have said that this works just fine. I can create 4 square roots of 1 modulo n, modulo any modulus that's got more than 2 prime divisors, except in the case where that modulus is twice a power of a single odd prime. So it turns out that that really is a description of the occasions in which I will not be able to find a primitive root. It's not so much a question of you don't have to have 2 odd prime divisors. It would work if you have any 2 divisors. One of them is an odd prime. The other one obviously has to be an even prime. But that even prime would have to be divisible by at least a 4. If it's twice the power of an odd prime, then there is a primitive root. All right, so that's this first solution here. This first theorem. It guarantees that, generally speaking, with a composite modulus, you'll be able to find more than 2 square roots of 1. I will remind you of how this is helpful in factorization. In the proof of this theorem, I went and manually constructed the 4 roots that I had in mind. If by whatever, let's say, a randomization technique, if you had just stumbled on if you stumbled on any solution to this problem, you already know about x being 1 or minus 1. But if you have another solution, then what you could look at is the GC, so I'll say note here. If you look at the GCD of x with, x minus 1 with n, then that would have to be some number that's bigger than 1 and smaller than n itself, unless x is equal to just plus or minus 1 mod n. If x is either of these 2 solutions to the problem, then obviously x minus 1 is either 0 or, let's see, then it would be, if x is -1, then this would be a -2. So when you compute this GCD, if the GCD of 0 and n would go all the way up to n. And if you're trying to factor, I'm going to assume you're trying to factor an odd number. You can always get started factoring an even number. But if you were trying to factor an odd number, then the GCD with 2, the -2 rather, would be 1. So those are the two extremes under which you'll be at one of those two endpoints. Otherwise, the solution x that you have found would have to be of this type for some pair of divisors for capital N. So when you look at, let's say, x3 minus 1, well, that would be congruent to 0 modulo b, but not modulo a. And so the GCD would have b as a factor and not a. So it would be the GCD of x minus 1 and n in that case would just be the b that I've written down here. So somewhere between 1 and capital N. So since the GCD is always a divisor of n, this is a method that helps people find divisors of big integers. Find some square root of 1 and then compute the GCD of x minus 1 with n, and you've started to factor n. Okay, so what does this theorem have to do with the claim that I made at the beginning of the hour? For that, I'm going to show you that if you do have a primitive root, if R is a primitive root modulo a composite number n, then in fact there exist at most d solutions to an equation of the form x to the d is congruent to 1 modulo n. So that would be in direct violation to what I wrote in this previous theorem. If you have a primitive root, you can't have this. So this should sound familiar. We already know that this, by Lagrange's theorem, this is going to happen in the case of having a prime modulus, but it's also going to happen whenever there's a primitive root. So you might have hope that there's other primitive roots for other moduli. Well, we know that they exist for prime powers, but what else? So first let me note that any solution to this problem, mod n, would actually have to be an invertible element mod n. So it lies not just in Z mod n, but it will have to lie in Z mod n cross. That's the same kind of a claim that I made earlier. I said I would come to it, and now I'm coming to it. It's an invertible element mod n, and the reason for that is since x times x to the d minus 1 power, just go down by 1, you will have created another element of Z mod n, which obviously then serves as the inverse of x. So here you've got, you've actually now got a formula for the inverse of that element x. Well, okay, so you're looking for solutions to this problem, and now you've just decided that they lie inside this, this subset of Z mod n. Well, if R is a primitive root mod n, then the powers of R are all going to be also in Z mod n cross. A primitive root is invertible for the same reason. And it's the lowest exponent on R that would ever get you back to being congruent to 1 is exactly the number of elements that there are in Z mod n cross. So all the elements of Z mod n cross are expressible as a power of R. So any such solution, it lies here, and therefore such a solution x can be written as that primitive root R raised to some exponent. And in fact, we know where those exponents have to lie. Starting at 0, you go only up to whatever phi of n is. So a primitive root is supposed to be something that takes this long to cycle through a lot of different elements of Z mod n until you finally come back to something you've seen before, which would be R to the 0 power. Well then, now we're looking to see what powers of R have the feature that this power of them comes back to 1. So you would have the equation that says R to the I times D would be x to the d which is congruent to 1. And that makes this exponent be a multiple of the order of r. That's kind of the definition of the order mod n of r. And the fact that r is a primitive root means that this order would be the same as phi of n. That was my definition of what primitive roots are. All right, so, well, how many such solutions are there if, well, so we need to, so I'll write it this way. I times d is congruent to 0 modulo phi of n. Now, if you knew that, for example, d was co-prime to phi of n, then you could multiply both sides by the inverse of phi of n, and you would discover that I just has to be 0. If I is 0, that would mean x is the identity element, and that would be just that's the one obvious solution to such an equation. In fact, that's the only solution when d is co-prime to phi of n. But in general, there's some common divisors between d and phi of n. In fact, there's really not any point in studying such an equation unless d happens to be a divisor of phi of n. But I'll run with it for any integer d. So then what could I say in this case? Well, you're saying that I times d is a multiple of phi of n, so why don't you throw away whatever common divisors you do have. Let's let e, say, be the GCD of d and phi of n. Then if I divide both sides of this congruence by that e, I have to divide phi of n by that e as well. So then what you would get is that I times d over e has to be a multiple of phi of n over e. But now e was the greatest possible common divisor between d and phi of n, and when I divide both of those things by their common divisor, now I've got two other integers that have no common divisors left. So that means that d over e is invertible modulo what's left of this modulus. So it has an inverse, and if I multiply both sides of this congruence by that inverse, now that says that I is congruent to 0. Well, if you like, it's 0 times this inverse. Nobody bothers. 0 times anything obviously is equal to 0. But I just wanted to stress that I multiplied both sides by the inverse of d over e, modulo phi of n over e. And so I've identified exactly what exponents I will work and when I got to this stage of the computation. The i's have to be multiples of phi of n over e. And you can use any integer that you like, but every exponent that I need is going to be in this range. So to keep the i's in this range, that means that to keep I between 0 and something means I should take k to be greater than or equal to 0. And the multiplier to put into this spot that finally makes this quantity as big as phi of n would be stopped before you get to k equals e. So this is exactly how many solutions I have. E actually is the number of solutions. So there exist e possible values for this number k, and every value of k gives me a corresponding value of I. So I have exactly e possible values for I, but every one of those i's gives me one of the solutions, x, to the problem that I started with. Oops, x. So the number of solutions to my original problem is exactly e, And since E was a divisor of D, that means that in particular E is less than or equal to D. So there exists less than or equal to D solutions X to the original problem. Okay, and that's the claim that I made at the start of this theorem. When you do have a primitive root, what you're saying is you'll never have more than dth roots of 1. And this is in fact a good way to characterize what it means for a group to be cyclic. The natural way to say it is you should be able to get everything in your set by just continually taking powers of just this one thing. And eventually when you take higher and higher powers of R, well, it's not there's not infinitely many different elements of this set. So they will eventually cycle back to R to something power will be the same as R to the 0 power. You'll come back to the identity element. So these collections of invertible elements, they're called a cyclic group. You cycle all the way through. And really what we've just decided in here is that the way to characterize them is that you should never have any more than 2 elements that you can get through this whole cycle by just taking 2 steps. You should never have more than 3 elements that will come through by just going up to their 3rd power and so on. Contrary to what I had when I had more than one odd divisor of n, and then I found that I could have 4 elements that just come back to the starting point after just a single squaring. So this is one of the ways to see that that there cannot be a primitive root if you have more than one prime divisor to your modulus. And I'm getting at the structure of how these groups of integers look. When you do have a primitive root, that happens when you do have an odd prime power, then there's only the right number of solutions to such a congruence. But when you're divisible by multiple primes rather, then you get kind of too many solutions. All right, so this all has to do with how do things look when you do have a primitive root, and see why that rules some other things out. Let me give you a separate proof of this theorem because I want to reinforce this other idea that you guys should get used to, which is when you are working with a composite modulus, more precisely a modulus that has not just a prime power, but you have multiple primes in there, you really should always just be thinking about the Chinese remainder theorem. The Chinese remainder theorem allows you to pry apart the conclusions that you get into the different prime powers that show up in your modulus. So let's have a different proof of this theorem that uses that idea. And you can think of this as perhaps a more direct proof of the fact that there is no primitive root. So let's have proof number 2 of the same theorem. So let's just suppose that our modulus is composite again, but more precisely, it's the product of 2 odd factors that are co-prime. Well, I don't know, maybe there's a primitive root out there. So let's think about what that would mean. If x is a primitive, well, r is a primitive root, what's supposed to be true is that that means that the order of r modulo n is supposed to be the whole maximum that it's supposed to be, that it is ever allowed. You shouldn't ever come back to the identity element until you've risen all the way to this exponent. Now that's the exponent that was guaranteed for us by Euler's theorem. So Euler was the guy who said, hey, take any element, any invertible element, mod n, and if you raise it to this exponent, I guarantee you'll come back to the number 1 mod n. At some point, you might have asked yourself, I wonder if you could ever get away with a lower exponent. Now, if you can, if you could prove something like Euler's theorem, but with a lower exponent than phi of n, then 2 things should occur to you. Number 1, you're better than Euler, and that's a pretty darn strong statement. if you're proving that there's an even a smaller exponent than this, which placed as an exponent on any invertible congruence class mod n would give you a 1. That would imply Euler's theorem, but your theorem would be stronger, so kudos to you. And the second thing is, if you could prove such a theorem, then that would automatically mean that there can be no primitive roots, because there would be no number for which you have to wait this long until you come back to the identity element. So I'm going to show that this can't happen by saying, I can show, we will show, we will, how should I say this? We will find a smaller number, an exponent capital M, which is smaller than phi of n, with the following property. It will be true that for all the invertible congruence classes mod n, when you raise x to this exponent, you'll get something that's congruent to 1 mod n, right? So Euler said that this kind of a statement will be true when m is equal to phi of n, but we're going to beat him. We're going to find a smaller number. It necessarily would have to be a divisor of phi of n, but our smaller exponent would also work. So once that's true, that means that the order of every single element mod n, every invertible element, is going to have to be less than or equal to this number m. So then, for all such x's, the order mod n of x can never be more than m, and so in particular, it's never equal to phi of n, and that means that you can't have a primitive root. All right. So how am I going to do this? How am I going to find this exponent capital M? Well, I'm just going to use the Chinese remainder theorem again. That's my favorite way of handling a modulus that I can split into two coprime factors. So I say to myself, well, if I want x to the m to be congruent to 1, all I need is for x to the m to be congruent to 1 modulo a and b separately. So it will suffice to find an m such that for all these invertible elements in Z mod n, you have two things. You want x to the m to be congruent to 1 modulo a, and at the same time, x to the m is congruent to 1 modulo b. Because then x to the m minus 1 is a multiple of both, and it's therefore, because of this, it's a multiple of their product, which is n. Well, I can do that. I mean, I could, at a minimum, use Euler's theorem to find such an exponent that would work in this case. So we do know that x to the phi of a is always congruent to 1 modulo a, because if you have a congruence class that's invertible mod n, it'll also be invertible modulo any divisor of n. In fact, you can use exactly the same inverse that you use mod n. That same integer will be an inverse modulo both a and b. So all the things that I'm trying to find an exponent for, they'll all be invertible mod a, and if you want to know an exponent that you can use for the congruence classes mod a, why don't you use just phi of a? And likewise, I know that x to the phi of b power will be congruent to 1 modulo b. Now, I wanted a single exponent that would apply to both of these things. So what I need now is to take any multiple of phi of a and any multiple of phi of b that would make these congruences true as well. So let me write it this way. X to the phi of a times k, that'll be congruent to 1 mod a for all integers k. And likewise, take phi of b to the L power. No matter what L is, you've got, this will end up being a power of x to the phi of b, so it's a power of 1, which is 1. So all I have to do is use capital M to be any common multiple of phi of a and phi of b. You might choose, for example, the least common multiple. After all, we're trying to find small exponents. So let's choose the least common multiple of phi of A and phi of B. Okay, well, that's cool. I mean, that's a nice general principle. If you want some power to be congruent to 1, you just need that exponent to be a multiple of the order mod A and the order mod B, and these will work. Of course, now I have the problem that I don't know how to compute an LCM of two numbers. Maybe I'd have to go start finding prime factorizations or something. That would be one way to do it. A faster way is, we did have a formula early in the semester for how to compute an LCM of two numbers. Anybody remember how that one went?
We multiply and divide by the GCD.
Yeah. So if you can find the GCD of the two numbers, that would work. Find the GCD and divide that into the product. That takes into account, this helps cancel off the sort of extra factors that you need, that you've acquired when you simply multiply these two things together. Now I can make this a little bit simpler, because I did assume that the numbers A and B were co-prime, and we have proved that phi is a multiplicative function. That means that phi of A times phi of B will be the same as phi of A times B, which that's phi of n there in the numerator. And then down below, I still have to figure out these GCDs. Okay, now I remind you that my goal here was to find a smaller exponent than phi of n that I might use. So I actually don't want m to be that big. And my formula for m now looks like it might be that big. Actually, though, it can only be as big as phi of n in the one case that this GCD down below is 1. It can only happen if phi of A and phi of B are co-prime. Otherwise, I can tell already that I'm going to win. So, I don't know. Can you find any common factors between phi of A and phi of B? I got an easy one for you. They're both even, because A and B are both odd, and the formula that we use, one of the formulas for the Euler phi function, is that phi of A, it's the product of the phi of all of the odd primes that are dividing A, prime powers, and when you take phi of p to the k, you know you get p to the k minus 1 times p minus 1. So for every odd prime that divides A, you're going to get a factor of p minus 1, which is even, as a factor of phi of A. So this will for sure have 2 as a divisor. In fact, there's a lot of 2's that divide this. If B is the product of, let's say, 3 different odd primes, well, for every one of those primes, p minus 1 is one of the factors of this integer phi of B. And so every one of them will then contribute another power of 2. So there's plenty of powers of 2 floating around in all of these things. So that means that the GCD of phi of A and phi of B is not 1. It's got to be at least 2. And therefore, my m, it's been computed in this way, it's going to be actually not just smaller than m, but it'll be at most half the size of phi of n. Well, actually, I did tell you, m, the smallest m that works will actually be a divisor of phi of n. So the biggest possible divisor other than phi of n itself would be this one. But you do get that, which is the win that I needed. I found a smaller exponent. I found a smaller exponent that makes x to the m congruent to 1 mod n, just because it works modulo both A and B. So Euler was kind of doing overkill. Euler told us that we could use the exponent, all these exponents could be phi of n, but we don't actually need it to be that big. And that sounds like a positive thing to say, but what it does mean is you ain't never going to have an element of Z mod n whose order gets that big. The order is going to always be this big or smaller. So, sorry, No primitive roots are allowed. And in fact, if you look at this theorem, I get my punchline down here by knowing that both of these, the phi of A and phi of B, are both even. So there's the GCD that goes in. All the rest of this stuff doesn't really pay any attention to whether A and B are even or odd. All I did need to know was that A and B are co-prime. So it's really all right if A and B have, if one of them is even, obviously they can't both be even, but if one of them is even, then all of this argument will still go through, as long as you do just have to know that phi of A is even. And if A is itself divisible by any odd primes at all, that's a win. And if it's not divisible by any odd primes, you might still win in the case where that number A is a power of 2. Our recipe for computing the Euler phi function here makes this be 2 to the k minus 1 times 2 minus 1. That's just a 1 that doesn't contribute any even factors like those guys had. But you might still get an even factor in here. In fact, you will, as long as k minus 1 is positive, which is to say as long as k is more than 1, which is to say as long as A is a multiple of at least a 4. So in this entire argument, I can show you that you cannot have a primitive root modulo n if you can ever write n as a product of two coprime numbers. In other words, if n ever has more than one prime divisor, with the one exception being if that divisor right there is just a plain old 2. And if b then is the power of a single odd number, then I wouldn't be able to use all of this argument and you could still have a primitive root. So I stated it up here at the beginning by saying that there's no primitive root if you've got more than one odd prime divisor. But now that you see that the same result applies if it has more than one odd prime divisor, or even if it's only got one odd prime divisor and then a power of 2 that's greater than the first power. Just 2 to the greater than 1 times p to the k. I'm sorry, that's kind of strange notation. But you get the idea, all right? So the only possibilities left are really the ones that we've talked about where n is a power of a prime, a power of an odd prime. There do remain a few other cases where n is just a power of 2, or where n is just the number 2 times an odd prime power. So just to clear those cases up as well, we've done n being a power of a prime, odd, p odd, and those do have primitive roots. We've talked about n being a product of 2 or more odd primes, and those do not have primitive roots. We've talked about n having a power of 2 times an odd prime. No primitive root there if k is more than 1, p to any power of a prime. So what's left is just what if n is a power of 2, or what if n is 2 times a power of an odd prime? And continuing the little pattern here, I'm going to put a frowny face for this one and a smiley face for that one. And the proofs are actually pretty easy. You can't have a proof, this is if n is more than 1. You can't have a primitive root modulo, let's say 8 or 16 or 32, because you can't even get a primitive root modulo 4. And it's exactly the same problem that we ran into here. You can't have a primitive root modulo a power of 2 because you can find more than 2 square roots of 1. And in this particular case, I can prove that for you easily. Obviously, x equals plus or minus 1. Both of those things are solutions to the problem of having a square that's congruent to 1 modulo this power of 2. But I can name 2 more. If you take x to be plus or minus, plus or minus 1, but then I add to it not this power of 2, but the previous power of 2. Solutions. That's an integer, obviously. As long as n is anything positive, then you'll have a power of 2 here, and add or subtract 1 to it. And when you go to calculate the square of that, obviously in this case it's trivial, but in these cases the square will be the square of the first term plus the square of the last term plus 2 times the first times the second. Well, when you reduce all of this modulo n, that's congruent to 0. And this will also be congruent to 0 as long as n is more than 1. Starting with n equals 2, this would be 2 minus 1 is 1. If you double that, you get 2, which is n. I mean, this could be written as n plus n minus 2. So you've got an exponent on the 2, which is more than the amount that you need. It's at least as much what you need as long as n is at least 2. So you've got too many solutions to a problem. You've got more solutions to this, more roots of this quadratic polynomial than just 2. And by a result that I gave earlier, that means there can be no primitive root. Starting with 4, a modulus of, starting with a modulus of 8, then this would give you 4 different roots. When your modulus is 4, then here I've listed the 2 solutions, plus 1 and minus 1. And here let's see, when 4 is 2 squared, so this would be 2 to the first power, that's 2. So now I have 2 plus 1, which is 3, and 2 minus 1, which is 1. And those are the same 2 roots that I have over here. So as soon as your power of 2 is more than 2, I'm sorry, I said 1. As soon as you pass 4, mod 4, there is a primitive root, but starting mod 8, this argument shows that you'll have different solutions, mod 2 to the n. And finally, this case here, I will point out that this is actually the same as this case over here, simply because in this case, phi of 2 times p to the n, where n is an odd prime, is the same as phi of 2 times phi of p to the n, but phi of 2 is just 1, so you have exactly the same number of elements in the multiplicative group mod n here as you do modulo this p to the n. So actually, if you just use the Chinese remainder theorem to take a primitive root modulo p to the n, take something that's congruent to that modulo p to the n and congruent to 1 modulo 2, well, that will be a congruence class that works modulo 2 times p to the n just as well as it works modulo p to the n. So that's why if you can have a primitive root modulo p to the n, you just make sure that you've chosen an odd integer that reduces modulo your primitive root, and that will serve as a primitive root with this composite modulus. So that's the grand total of all the possibilities. If you want to work just with even primes, you have a primitive root if n is congruent to either, well, 1, I guess there's nothing there, mod 2 or mod 4, or a power of an odd prime, or twice a power of an odd prime. These are exactly the cases when you get a primitive root, and every other modulus, there's no primitive root. All right, I'm going to spend one more day on Wednesday discussing the primitive roots, and that I hope will actually get you a little interested in this stuff again, because what it enables us to do is to actually compute things like logarithms. We're going to fix a primitive root. We'll choose a modulus that's one of these so that we can find a primitive root. And then we'll be able to work with this figure. If R is a primitive root, we'll be able to compute logarithms in the sense that you can write every invertible x, I'll say invertible, is of the form x equals r to the I for some I. This I, it's a kind of a logarithm. The word that we will use is that it'll be the index mod r, or base r, of this x. So you should think about that as being something like taking a log base r of x. So I'll show you what we can get as a consequence of that concept on Wednesday. Oh, and how about that? I haven't even gone a minute over yet. Does anybody want to ask me some questions about these parts of the proof, or the general idea of what we're getting out of these primitive roots? No? Good, good. All right, so come back on Wednesday. I'm going to show you some of these kind of logarithm calculations and what we can do with them. Turns out people use these as both for kind of cryptography applications and also as like a testimony to their computing skills, because finding out these indices, that's kind of a hard task in general, and I'll give you an explanation as to why that's so. All righty, guys. Try to finish your homeworks by Wednesday as well. I'll give you one last chance to ask me about them when we come together on Wednesday. And if you have any other questions, come meet me in office hours.
Thank you.
See you on Wednesday.
See you then.